Good afternoon. I am Hunter Enders, and I am a junior computer engineering major in the Randall Research Scholars Program, working on antenna array simulation and fabrication for UAV-based microwave remote sensing of soil moisture. This project is under the direction of Dr. Neshani in the College of Engineering's Remote Sensing Center. Soil moisture. Too little moisture can result in too much moisture. Soil, it can ruin the integrity of the terrain. Accurate measurement and representation of the soil in order to irrigate and make. Our main goal for this project is to design a tightly coupled antenna array for a UAV-based radar system that will encourage better results that can be used to make the best decisions in precision agriculture. This presentation will provide background information related to our work, presenting a starting point for our research and other information we have considered. Some of the goals created to lead us to our intended outcome will be shared. Our approach to meeting our goals and the steps we have taken along the way will be presented, logging our progress. We also will present various figures and output plots to show our results and explain how they impact our decision-making process. Key takeaways to this point will be shared in order to indicate any notable discoveries or problems encountered. And finally, we'd like to present our future work plans and any updated goals to show what remains on our path towards success. As mentioned in the introduction, this project aims to create a microwave radar system mounted on a UAV. This system should have broadband coverage and high-resolution imaging capabilities despite potential obstacles that may be in the way, giving accurate readings that will be valuable in precision agriculture. Using the article VHF-UHF Ultrawideband Tightly Coupled Dipole Array for CubeSats, published in the IEEE Open Journal of Antennas and Propagation, we formulated a starting point. The paper describes a tightly coupled dipole array designed for satellite imaging that is 1.2 meters long, 10 centimeters wide, and 1.5 millimeters thick. Additionally, it has a voltage standing wave ratio less than 3 for the range 80 megahertz to 600 megahertz, and this value is below 4 when the frequency range extends to 65 megahertz to 600 megahertz. Additionally, across the frequency range, the active average reflection coefficient was negative 6 dB or lower. We would like to further optimize this by increasing the frequency range to 50 megahertz to 800 megahertz and drop the VSWR below 2, as well as have an active average reflection coefficient of negative 10 dB or lower across this frequency range. Therefore, we need to look into things like the dimensions of each element, the number of elements included in the array, and we hope that by optimizing this, we can increase performance and the frequency range of which the antenna can work. Using COMSOL Multiphysics 5.3 and 6.2 software, we created a workplane design, as can be seen in the image on the right. This design is called a unit cell, and each unit cell contains 2 dipoles, one of which, in the center of which is a lumped port. The table included here has parameter definitions. These definitions determine the dimensions of the unit cell and things within them, such as the length of a dipole arm, as well as the electrical properties of the antenna. Some of these parameters, especially those that govern electrical behavior, are maintained from the original design, while others have been changed as part of our optimization process. Some of our methods in order to optimize the unit cell include brute force, which involve making incremental changes, and each time a change was made, running a COMSOL study to see the impacts. Another is to use the parametric sweep tool. This looks at outputs for one input that is varied over time. It is similar to brute force, although it is more automated. An example of the parametric sweep would be finding the optimum spacing between dipoles in a unit cell. Put together, the unit cells make up an array. The array in the images provided on screen includes 10 unit cells, but more or less may be needed to fit the exact specifications of a given antenna. For instance, we have considered ourselves having 12 unit cells in our array, with the center 4 being active and the rest passive. But for our purposes, we believe an array of 10 unit cells is appropriate. And as you can see in the middle image, the array is contained within a box-like shape. This is called a substrate. Now the substrate we have here is a box, but it can be modified to have different dimensions, and it can also be in other shapes, such as a sphere. For now, though, we believe the box shape is an accurate model for the way our antenna will be implemented. A good way to determine the value of a change to the unit cell design is to examine the VSWR plot, as seen on the left. The voltage standing wave ratio, or VSWR, is the ratio of the maximum to minimum voltage on a transmission line and indicates how well the impedance of the load matches the impedance of the transmission line. The lower the VSWR, the more power there is delivered to the load. This plot shows the VSWR range values over our given frequency range. And as mentioned earlier, we would like for the entire range to have VSWR values under 2. This plot shows this, so we believe that our unit cell design is appropriate to meet the criteria we have established. Next, the average active reflection coefficient is analyzed over the frequency range for the entire array, as seen in the plot on the left. The reflection coefficient measures the ratio of the amplitude of the reflected wave to the incident wave, and essentially determines how much of the signal is reflected back. We hope to have reflection coefficient values below -10 dB for the entirety of the frequency range. However, as can be seen, this is only the case for the frequency values in the middle of the range. The lower and upper bounds are not below -10 dB. In order to change this, we can look at things like the size of the array, the number of active ports, or even which ports are active. The dimensions and shape of the substrate surrounding the array may also play an impact. These are all factors that we are going to look at as we continue to further optimize the design. We can also look at radiation patterns to determine antenna behavior. The expected radiation pattern for a dipole is a figure 8 shape, which is largely demonstrated by the image on the left. The closer the pattern gets to the edge of the outer circle, the greater the far field gain peak, which measures the efficiency of the dipole at that given frequency. For the lower frequencies, the gain is largely uniform. However, some deviation can be seen for higher frequencies. Take 700 megahertz, for example. The pattern at 90 and 270 degrees stretches outward. This indicates directionality in the antenna, where energy is radiated more in a specific direction rather than being uniform. This is the power of using a dipole. The wide band spread of the frequency range allows for both the uniform coverage of the lower frequencies as well as the focused coverage of the higher frequencies. Our research has shown us several variables that can sway the simulation results. First, the geometry of the unit cell heavily impacts impedance and wave reflection. This includes both the dimensions of the cell and the shape of the regions, such as the connection of the dipole arms or legs. It matters if we use a triangle or if we use a semicircle. The size of the antenna array also plays a major role. We believe that more unit cells could add to the power, but being we're going to implement this with a physical system, there are volume limitations that must be taken into account. And finally, we have to look into port coupling. Some ports, if we excite the center ports, they work together and they can boost low frequency performance. But if we excite too many ports and not enough terminate, there can be unexpected behavior and it can be difficult to track the radiation pattern. Our 5-step plan to describe our future work involves optimization, evaluation, fabrication, testing, and improvement. We would like to further expand the lower frequency bound from 100 megahertz to between 50 and 80. Once we have that, we will evaluate antenna gain, size, and bandwidth to ensure the design is ready for fabrication. And with the design brought to life, we can use it for field testing, ensuring the antenna works properly and pairs well with the UAV. From there, we will continue to optimize and implement improvements as necessary. Thank you for your time and attention. I'd now be happy to answer any questions.
Why did you choose to use a tightly coupled dipole array for this specific application?
Good question. So as mentioned, we followed the paper in the IEEE article. And if you have a dipole array, it allows coverage for ultra-high and very high frequencies. So you get that wide range that I mentioned earlier. Also, dipoles are omnidirectional. So yes, at higher frequencies, the energy may be directed in one direction more than others, but for the most part across the range, the energy is pretty uniformly distributed. Makes it very effective for penetrating obstacles like foliage if we're trying to use the drone high above the ground and measure the soil.
I think it was one of your first slides, but you showed like the array should be like 1 meter long or something like that when it's on a CubeSat. So would that then unfold when it's deployed? And if so, is there any impact on like how you design your unit cell?
Absolutely. The design is created so that it can be folded into several sections. And this was particularly created because of the original intent was to use it in a CubeSat up in space, and they wanted to be able to put several arrays in one small area. So we also would like to keep that folding functionality, and perhaps that means we can use multiple arrays as well when we put the antenna on the drone.
Will the antenna be versatile and fully functional in differing types of soil and terrain?
That's a good question. We believe it will, and that's because the dipole mentioned, the original design, said it was useful for various things. Yes, soil moisture, which is our purpose, but also looking at things like how deep snow layers are. A lot of antennas you can actually calibrate for the type of soil you want to use it in. I'm not sure how much of that we'll have to do, but that is something we'll have to take into account and look in our optimization process.